to you Dr. Toby Ault this morning, who is an assistant professor of Earth and Atmospheric Sciences at Cornell University. So Toby, thank you so much for being our guest speaker and introducing us all to the concept of springcasting. Feel free to take it away.
Okay, thank you. Thank you, Teresa. And I think, like everyone listening today, I'm honored to be part of this really important project that is NPN and the efforts of you, who are the observers, and trying to advance the science that will allow us, within, I think, a fairly short time to make more accurate predictions of the timing of spring. Of course, when doing a webinar on springcasting, you get asked very often, well, when is spring going to occur? And I think that there's an interesting point there, because all of us on some very basic level know that spring is not just the calendar definition of spring onset, March 21st. It's something that changes from one year to the next year. We talk about this colloquially. We say that it was a late spring or early spring. And so what we're working on are the tools to be able to monitor the progress of spring in real time using observations and data from meteorological sources, so weather data, as well as make forecasts. And what we're shooting for is a few weeks ahead of when spring actually occurs. And it's really going to have to be a community-driven effort where there's a back and forth between the scientists who are working on the models and the data informatics side and the observers like you who are out there telling us whether or not what we're doing makes sense with what you're seeing. So let's back up a second. What is spring? What is spring onset? And spring is, one of those things that you know it when you see it. All right, so it gets warmer, and maybe the plants start coming out of dormancy, animals start to migrate, people start wearing less clothing, and maybe if you're one of these northern states that's getting snow and sleet and ice and rain week after week, you start to feel less horrible about everything. So that's a good indicator of when spring is starting to happen. And as I said before, one of the things that really characterizes spring onset is that there are these year-to-year variations, which I've just shown schematically here with this diagram. The timing of spring one year is different from the year before and different from the next year, and maybe there's some long-term trends on top of that. Now, at the same time, another characteristic of spring, and this is widely recognized by people especially living in the middle to higher latitudes, the onset of spring tends to occur across reasonably large spatial scales, so geographic scales of a state or a few states. I'm from the Northwest originally, so this is a diagram from the Northwest. And what I think is important to recognize is that if it's spring in some parts of your state, if it feels warm and balmy and people are taking off their clothes and the plants are coming out of dormancy and the animals are migrating through, it's probably happening in other parts of your state as well. So we've got these two things that we think are really important for characterizing spring onset. We've got year-to-year variability. That's one. And large-scale coherence, large-scale patterns of the timing. And taken together, that's really the hallmark. That's the footprint of something interesting happening in the atmosphere, something interesting happening in the climate system that paces the onset of spring. So I want to show a little bit of data to try to wrap our heads around what it is that we're trying to characterize. What is that footprint? And how do we turn it into an indicator, a model of spring onset, particularly focused on the lilacs. And certainly when the lilacs start to put on leaves, that's an indication that it's the earlier part of spring. And when the lilacs start to bloom, that would probably be indicative of other types of events in that same window, maybe in that same week of spring onset. So this example that I'm about to show you is actually from a weather station that's been around for quite a while. It's just 1 year of that weather station. And it's going to be minimum temperature and maximum temperature. Minimum temperature in blue, T-min, and maximum temperature in red, T-max. This happens to be an old station from Jacksonville, Illinois. It's been around since 1869. It's the first year of that station. And there's some ups and downs that reflect the weather pattern that they pass through. This is daily data going from January, February, March, and then into April. And I want to draw your attention to something that tends to happen in spring, and you know these events. Anyone who's who's lived through any kind of winter recently in the Northeast is very familiar and probably looking forward to these kinds of events. These are the warm events that characterize, they signal something fundamental, a transition in the atmosphere, where suddenly the temperatures shoot up much above what they've been, and it's warm, and it just feels good for a few days. And maybe that happens in March, maybe it happens in April. It depends geographically, it depends on where you are in the United States, but it's one of the key indicators of the timing of spring. Also, of course, the days are getting longer. Also, snow is melting. These are the parts of the physical climate system that are indicative of spring. And even 5-year-olds will recognize this. They'll be able to tell you what it is that makes spring feel like spring. So with really a few decades of research now, and pioneered by Dr. Mark Schwartz, who is at the University of Wisconsin-Milwaukee, he was able to develop a model of lilacs and honeysuckle, 2 different species of honeysuckle and lilac, that was just very accurate at being able to pick out this window of time and turn that into an index, turn that into a day of the year in which we would expect those species, particularly the lilacs, to be coming out. We've taken his model and extended it to be able to, you can think about this as being calculated at every point in the whole North American domain. So like at every grid point, imagine if we had clone lilacs growing at every pixel in this map. Well, that's what we're trying to model. That's what we're going after, and that's what we need your help with for validating. So let me play this animation here of 2014. So last year, it starts in January 15th. The bar at the bottom is going to fill up, and then you're going to see the progress of this model of spring onset, the spring indices, move from the southern regions, which experienced spring earlier, to the northern regions. That's what you're going to see in this animation. This is last year. Those of you living in the Northeast and central U.S. will notice that when we get into March, middle of March, you might remember this, things really seemed like they were stalling out. We're really waiting for that line to creep further north, further north. By the time we got into April, it was actually our alumni weekend here at Cornell. We started to have those really balmy, warm days. And then, of course, it went back to being cold again, and spring continued to progress. Now, when this map is completely filled in, the colors are the day of the year. So each color corresponds to the day of the year, and that's shown down here by this bar. That was 2014 from the model. Now, 2012 was a really exceptional year, and I'm going to show you the animation for 2012 because it didn't look very much like 2014. Watch carefully. It starts about the same in the southern part, but watch what happens, and those of you who know where this is going, look in this area, what happens in 2012, right when we get into March. Wait for it. It just screams up. And this was the great warm event, the meteorological March madness of 2012. It brought plants out of dormancy. There was a normal freeze event in April of 2012 that because spring had started so soon, because it brought plants out of dormancy so soon, created a false spring. In Michigan alone, there was about $500 million in agricultural damage. So having these kinds of indices to track the timing of spring and the variations across the continent through time is really a powerful tool, not only for the, I guess, aesthetic value of the plants that we care about, and the birds, and the activities that we care about, but also there's an economic value to getting this right. And it really improves the more observers we have and the more observations we get. Just to drive home this point, I'm comparing April 1st from 2014 with April 1st from 2012. And the comparison is not quite perfect because 2012 was a leap year, so I should actually be comparing March 31st with April 1st. But notwithstanding, the maps look very similar for March 31st and April 1st for 2012. And what you can really see is that the onset of spring was many, many days earlier. In some regions, the difference between the timing of spring or that fall spring in 2012 was 40 or 50 days different from 2013 and 2014. So what's going on? What's happening in the atmosphere? Before we get to what's happening in the atmosphere, I want to show you one more animation of things on the ground. These are just average temperatures. This happens to be 2009. And 2008, 2009. It starts in 2008 in the fall. The colors here are warmth, so the temperature in degrees C. And you can see as it's getting into October, there's less warm regions, there's less warm temperature. There are fewer temperatures that are warm. And then the cold polar air masses through December, and January and February when they come up are gonna break out from the Arctic regions into a lot of the North American domain. These are daily temperature averages. You can already start to get a sense that things are moving with the weather from the west to the east. They're moving in this direction. As we get into spring, now here we are in spring, you start to see those warm air masses creep back to the north. Like I said, this just happens to be 2008, 2009. I picked this year because it was kind of an average year and reflects a lot of the things that are important to understand in terms of the weather patterns driving the transition from winter into spring. Now we're getting into really late spring, May, summertime almost, and this vast region of warmer, more favorable weather for growing plants, growing crops has emerged. And we get into the summer, and the animation will end at the end of August. All right, so that's what's happening on the ground. That's what we feel on the ground, and it's okay. It's not everything we want to know, because we also want to be able to characterize something about what's happening in the atmosphere. Now, if you think about the atmosphere, you think about our planet is receiving most of the energy from the sun in equatorial and tropical regions. That makes the tropics very, very warm. And warm air takes up more space than cold air, right? Greater volume. So at the first order, think of the tropics as being very warm, of course, we all know that, and also maybe taking up more volume because they're warm. At the same time, we in the atmospheric sciences tend to use a special kind of layer to characterize the top of the atmosphere, or close to the top of the atmosphere. Think of this like a sheet. So we're going to show in the next animation a sheet that's going to be higher up towards the tropical and subtropical regions and slope down as you get closer and closer to the higher latitudes. So as it gets colder, that sheet's going to be lower down because it's a colder air, it takes up less space, and that sheet's going to be higher up as you get into the subtropical regions. That's what's going to be in the next animation. So here it is. This is the sheet that I was describing to you. Higher heights of this marker of an important part of the atmosphere, and lower heights as you move towards the higher latitudes. This is the North American continent down here. So you can imagine that we are watching this animation from somewhere maybe positioned in a satellite well above Alaska. On the vertical axis here, we've got height in kilometers. So just watch what happens as we go through the annual cycle. Same year, starts off in the same way as the previous animation in September. You've got very high heights in the tropics and subtropics, all the way extending over most of North America. As the northern hemisphere begins to cool from shorter and shorter days, the height of that sheet that seems like it's blowing in the wind gets lower and lower, all the way through November and then December. But look at the subtropical regions over Mexico. The height isn't changing by as much. And because it's not changing by as much, the gradient, the slope from the subtropical regions out to the polar regions is actually intensifying. And just like in an analogy to water, water is going to flow downhill. Well, atmospheric mass is going to tend to flow down this gradient. Think of this as being a gradient where atmospheric mass is going to be transported from the equatorial regions to the polar regions. But that's not the whole story. You can see it's weakening as we get into spring now. It's not the whole story because we have a rotating planet. Because of our rotating planet, anyone who's familiar with trying to walk across a carousel or a merry-go-round and understands that it's complicated. It's not so straightforward to walk on a rotating disk, just like atmospheric motion is complicated by the rotation of the Earth. And in our case, the way that our Earth spins, it's actually going to deflect that motion of atmospheric mass, of wind, right, of air, towards from the west towards the east. It's going to deflect that, and it's going to organize it. It's going to organize that flow into a jet stream. So you've heard about the jet stream on the Weather Channel. Well, I wanted to show an animation of the jet stream, which is what's next here. What I've done is I've contoured the winds at the upper level of the atmosphere. Think of these as riding right along that curtain, that sheet that we saw before. And it's going to intensify through the winter season and then break down in the spring. Again, remember, the flow, the direction of atmospheric motion is from the west over North America towards the east. So it's going through this tube as it wobbles around. And there's some waviness, and the jet loses its coherence and structure. But in general, it's starting to intensify. It does intensify as we get into the winter season. December, and then really it's roaring, it's racing once the gradient is at its maximum in January and February. And it's so strong that it's actually the place where I truncated this data volume ends up capping off the top of the jet. And as we get into March, it weakens again, and it decays, and it starts to break apart. And on the ground, we feel the influence of this. If we go back to that animation before, this one, and we just fast forward it to, say, let's go to March. You can think of the position of the jet stream and this gradient governing the difference between the warm subtropical air masses, the warmer air coming from the south here, and the colder air breaking out from the north air. And there's a jet stream somewhere in there, and there's a gradient that's changing in the springtime. And that change in that gradient fundamentally shapes the weather we experience and the timing of spring from year to year. And this has to do with our planet and its orbit around the sun. Now I'm going to take a bit of a detour because I want to come back to something really important, really integral to our understanding of spring. And you'll see why. But I want to take a little detour and go back in time about 100,000 or more years. So from right here, where we are now, we experience summer, northern hemisphere summer, by the long days. Right? So in the northern hemisphere during summertime, days are longer than in the winter. But at the same time, we're actually furthest in our orbit from the sun. We have long days, but we're furthest from the sun. So the summer equinox, the summer solstice, the longest day of the year, the summer solstice in June, happens at a point when we're actually farthest away from the sun. 10,000 years ago, about 10,000 years ago, that wasn't the case. We were actually closest to the sun. One of the questions that always comes up about climate change, when one studies climate change or talks about climate change, especially up here where it's been this brutally cold winter with lots of snow, people want to know, well, what was happening 10,000 years ago? What was happening with the last ice age? What about the time when there were mammoths and giant sloths? I mean, what's up with that? Where does that factor in to our understanding of climate change? Well, I'll show you a couple points that are relevant to that exact question. 10,000 years ago, we were at a point where we were closest to the sun during the northern hemisphere summer. That meant there was more solar energy hitting the northern hemisphere. And at the same time, 20,000 years ago, so 10,000 years before this diagram would be applicable, 20,000 years ago, we were at a period known as the last glacial maximum. Ice was covering most of the North American continent, at least the northern latitudes of the North American continent. And you can see that here. Siberia as well. And these huge ice sheets. Right where I am today in Ithaca, New York, in the Finger Lakes region of upstate New York, we would have been underneath about 2 miles of ice. 2 miles of ice. So next time you're in a plane and you hear bing, bing, and it's 10,000 feet, it's okay to use portable electronic devices. That's about the height of the ice that would have been over top of us, right where I'm standing today. This movie shows deglaciation from that period of maximum glacial extent through about 6,000 years ago. And you'll see those ice sheets just erode away and leave behind the lakes that we have. This is a cycle that has happened at least 4 or 5 times before. It's a cycle where the northern hemisphere grows gargantuan ice sheets. Sea level drops globally, and then it recovers. It's a cycle that has a 100,000-year beat to it. Most of the plants and animals alive today had to find a way to cope with that extreme variability in climate. They had to be able to cope with the climate changes that have occurred over the last few tens and hundreds of thousands of years, and the very different configurations of the Earth's orbit, the position of the glaciers. That includes the plants that we're monitoring, that we're interested in, and it includes us. I mean, we are a creative, adaptive species that learned how to cope with this extreme climate variability by building and using tools, having complex social networks, building fires, using fires to stay warm. Other species had other adaptive ways of dealing with that extreme climate variability on these 100,000-year timescales. So now you might be asking, well, why 100,000 years? I mean, what does that have to do with the pace of these cycles? The 100,000-year cycle of glacial extent, growing northern hemisphere glaciers and melting them away, this 100,000-year cycle is related to the shape of the orbit and the timing. So the shape of the orbit changes to become more elongated like it is today and more round like it once was. More elongated, more round. That's a 100,000-year cycle. The timing of northern hemisphere summer doesn't matter when it's round. It matters when it's elongated. And so when it's elongated, you can melt off those ice sheets. This is a temperature record from the Antarctic ice sheet. This is a core of ice that drilled down into the ice, going back 400,000 years. And you see this 100,000-year beat. We're in the warm period of today. It's called the Holocene, from about 10,000 years ago through today. The last warm period, the last summertime of these interglacial glacial cycles was called the Eemian, and there were several others just over the last 400,000 and some odd years. Okay, so where am I going with this? What's the implication for spring onset of these glacial and interglacial cycles? Plants are really, really smart. Something about lilac, other plant biology, phenology, has tapped into the information available to them from the atmosphere alone, from the atmosphere and the land surface. They've tapped into the information despite these wild fluctuations of glacial and interglacial cycles. And that's what we want to know. We want to know what the plants are picking up on in the atmosphere so we can, A, understand the atmosphere better itself as a dynamic, interesting quantity, B, make better predictions, better forecasts of spring onset, C, understand how climate and evolution have occurred over the last hundreds of thousands of years, and finally, and really relevant to adaptation and growing plants, growing crops in this century, we want to understand what's going to happen with climate change now. Climate change now is occurring. It's a function of the fact, it's a consequence of the fact that we're putting more greenhouse gases into the atmosphere. The idea that putting greenhouse gases into the atmosphere would warm it has been around for quite some time. This is Svante Arrhenius. He was a Swedish physicist, the late 19th century, and he predicted that because of the Industrial Revolution, the increase in greenhouse gases like carbon dioxide, CO2, would warm the planet. And of course, as a Swede in the late 19th century, he probably thought this would be a good thing. Now, let me say, greenhouse gases by themselves, and I don't have a political agenda here, I want to make sure that it's clear. Greenhouse gases by themselves, not a bad thing. Having greenhouse gases in our atmosphere keeps it looking from this, like this. This is what our planet would be. This is the Enceladus, the moon of Saturn. Our planet would probably look more like this without any greenhouse gases. It'd be a cold, frozen, watery wasteland underneath. It would have almost no atmospheric moisture. It would reflect much more sunlight out into space, and it would be frozen. The only life that would probably exist on this kind of a planet would be near the thermal vents at the bottom of the oceans, where warmth from the actual mantle would be bubbling up. That's not the planet we have, thanks to greenhouse gases. So on some basic level, we have to say, yay, greenhouse gases. They keep our planet habitable, not too warm, not too cold. But we're putting more of them in the atmosphere. So what happens then? I want to go through the basic physics in a really simple way, because I think the basic physics are easy to grasp, and yet most people who talk about climate change with and without political agendas, and of course most people do have a political agenda, either on one side or the other of the debate. I want to stay out of the politics, and I just want to talk about the physics. And if you can imagine the situation where it's a cold room and you've got your hands around a candle, or let's say you stick a rod into a hot fire, a metal rod, and you let it heat up till it's red hot. You pull it out and you put your hand next to it. You feel that warmth. It's not the air. It's not the air that's warm. It's an invisible light source that you can't see. It's electromagnetic radiation. It's invisible light coming off of that hot rod, or coming off of that candle that's warming your hand. This light that we can't see is fundamental to our understanding of the physics of climate change, of global warming. Let me show you some examples of this light that you're probably familiar with. This is from thermography. Thermography takes the invisible parts of the spectrum. To our eyes, we can't see this infrared radiation. We can't see heat. We only see other parts of the spectrum. But we can take that invisible light, which can be detected by certain types of cameras, and shift it over into a part of the spectrum that we can see. That's what's being shown here. This is a cold night, and it's just looking at two different buildings. Coming off of this building, which probably has much worse insulation, there's more light. There's more heat leaving as electromagnetic radiation, leaving as invisible light. This one, that light's only coming out of the windows. Probably better insulation in this wall. This is a steam engine. Very bright. Lots of heat coming off this thing, of course, as you'd expect. This is a snake wrapped around a man's hand. Humans are warm-blooded. Snakes are not. More light coming from the heat source of this man's hand. And here's a picture of a cat. Apparently the top of the cat's head loses more energy in this invisible light than the rest of the cat. The fur traps that heat in. The fur traps the heat in much in the same way that greenhouse gases trap that invisible light out of our atmosphere. That's the greenhouse effect. It's just saying that because we have these things, greenhouse gases, water's one of them, carbon dioxide's another, methane's another, the energy leaving our planet as invisible light, as heat, has to slow down. It gets trapped. It comes in very easily, and it leaves very slowly. It leaves with more difficulty than it comes in. And because it leaves with more difficulty than it comes in, that energy gets trapped in the atmosphere. We experience that as warmth. Putting more CO2, putting more greenhouse gas into the atmosphere just slows that whole process down. Doesn't really change how we get the energy, but it changes how we lose it. We slow it down. We lose the energy more slowly, and we experience that slowdown. Like a cat with more fur, we experience that slowdown as warming. That's the basic physics of the greenhouse effect. Now, what that means for this century, it means we're going to see some warming, or a lot of warming this century. How we get there is an area of active research in my lab and many, many hundreds of labs and universities and institutions across the world. So far, the change in this imbalance is about 2 watts per meter squared. This is the unit that we use to measure energy changes from these radiative effects. So what's 2 watts per meter squared? Well, it's about the same radiative effect as the heat, the energy going down from a well-lit Christmas tree planted on every square meter of the whole planet. So if you integrate that, you think about, okay, one well-lit Christmas tree, the heat energy of the light from one well-lit Christmas tree on every square meter of the planet. If you integrate that up, we've got a pretty big planet. It actually adds up to the equivalent heat energy of 4 atomic bombs per second. That's the imbalance. So there's an imbalance in the energy that the Earth is absorbing because of this greenhouse effect, because of the human contribution on top of the existing greenhouse effect. You can think about this differently. If you start a water kettle boiling, an electric water kettle boiling, there's more energy going in than is coming out, and the net change has to be that the water heats up and boils. That's what's happening now. There's more energy coming out. There's an imbalance in the energy of the Earth climate system that's producing this warming. Okay, we're in the Northeast. I'm in the Northeast. It's cold. It's been a cold winter. It's been a bit cold couple of winters now. So I just wanted to show a global map to put what's happening in the Northeast in a bit of context. This is for January. You can really clearly see that although we, in the most populated part of the U.S., might be experiencing cold or average conditions, a lot of the world is not. And anyone out in the West Coast is familiar with this. My parents live in Oregon. I said I'm from the Northwest. My parents still live in Oregon. They said their rhododendrons were coming out in like the end of December, January. So what we're seeing here is just a little cold patch. And I think February is going to look even more cold, even more focused around the Northeast. But we're still going to see this really crazy warmth in other parts of the world. And it's what you would predict, theoretically, just knowing about the physics of the greenhouse gases, which you now know about. So what's next? Springcasting. Let's get back to springcasting. Before I show you what we've put together so far, I want to give you an overview, a little bit of a roadmap, and my basic philosophy on what we're doing and how we're doing it. So I think of climate change being like a dark road, and somewhere, at some point, the conditions are going to deteriorate, right? The road is going to get worse if we keep going down the path that we're going with increasing the amount of carbon dioxide in the atmosphere. And it's beyond, it's beyond my area of expertise to comment on how we should proceed. I don't have a roadmap of some other alternative route. I don't have any particular insight into what we can and should be doing beyond what I think is reasonable for myself to do. I bike to work, and I'm mostly a vegetarian, except for the holidays and when I'm staying at hotels that have free breakfasts with delicious bacon. Other than that, I don't really eat very much meat. And by biking and not eating very much meat, I reduce my own carbon footprint a little bit. But it's a global problem. This is something that the Onion, the fake news source, the Onion, said that climate change has been attributed to 7 billion unique individuals. I think that captures in essence of part of the problem, and that there are many of us who are using greenhouse gases for the improvement of our lives and livelihoods, and yet that effect on the climate system is starting to be felt and could be really profound as we move into the future. So what do we do? I mean, how do we, who aren't in any type of political arena to try to affect change, cope with this? And I think one of the ways where we can play a strong role as a community, all of us really, is investing in brighter headlights so we can see what's coming. We can see when it is that we need to slow down. And that's where springcasting and where your observations really come into play front and center. Because what we're working on is predicting the timing of spring on year-to-year timescales, but under climate change. And so the models that we have today of the first leaf of the lilacs or the bloom of the lilacs or the other species that we're interested in, but just starting with those lilac observations that are so rich in their long temporal coverage, just starting there, what we could say, what we want to do is want to extend that to other types of species. And we want your help because we don't know if it's going to be the same kind of model that we need in the future that we've been using now because of climate change. Here's what the web page is going to look like. It looks like now. It's live. So you can go in and you can see our predictions so far. This year, what we're doing is we're trying to track in real time or near real time the progress, the propagation of this first leaf index for the lilacs. I run them, usually I run it on the weekends and try to update the maps every Saturday or Sunday. So this is from this weekend when I ran the model the last time. So this is the current state. So probably if you're in the West, it started to feel like spring, maybe with some of the southeastern states as well. We're going to update this week by week. So by the end of this spring campaign, we're going to have the same kind of animation for 2015 that I showed you before for 2012 and 2013, 2014. Those are all also archived on this web page. You can go to it. And I invite you to go to it and tell us what you think. Especially, as we ask you for your observations, the sooner we get them, the sooner we can overlay them onto this kind of a map and just see how we're doing. The other side of this, of course, is to work on the forecast part. That's a longer-term project. I think by next year, we should have actual quantitative forecasts with uncertainty, and that's really important, understanding the sources of our forecast skill and our uncertainty. We're working on using this very new data set. It's coming online now. It's a phenomenal amount of data, but it has the potential to be extremely powerful. It's called the National Multi-Model Ensemble, or NMME. And this is brought in part by Ben Kirtman in Florida. It's a collection of global, fully global climate models, the ocean, the atmosphere, everything tied together to try to make forecasts, like weather forecasts, but out to 10, 30, 90 days, seasonal predictions. We're starting to try to use that to forecast spring onset. And the good news is, talk about what is spring? Well, spring is, in part, things that are completely determined by the current orbit of the Earth, the length of the day, for example. We don't need a global model to predict the length of the day. We're getting that for free. We're getting the average background warming from climate change as well. And so those two things give us a little bit of hope, a little bit of more opportunity to make accurate and skillful seasonal predictions, especially with the community's help in observing what's going on the ground so we can update and improve and ingest that information into the model as we develop it. So there's this National Multi-Model Ensemble, NMME. It's a huge archive. We're talking about daily data from 10 different modeling centers around the world that are run in forecast mode, I think at the beginning or the middle of each month, for 100 different simulations. So if you do the math, it adds up to really hundreds of terabytes or petabytes of data that we're trying to comb through to assess the potential predictability of spring onset. That's just on the data side, the modeling side, and then we're comparing that with the observations as they're coming in. We're really looking for, and we're really interested in the idea that there might be changes in the actual responsiveness of the plants because of changes in the statistics of the atmosphere due to climate change. So the historical record isn't enough. We need to ingest, we need to incorporate new observations as they come in year after year. But in the interest of making a preliminary attempt at springcasting, at our first real forecast for the, I should say, if it's right, it's NPN and ECRL. My lab is ECRL, the Emerging Climate Risk Lab. If it's right, it's NPN and ECRL. And if it's wrong, it's just me. It's only me that blew it. So this is what the NOAA sees. This is the NOAA Seasonal Outlook. This is one of the products that they use to make seasonal predictions and distribute the information. The coloring here is not the actual temperature anomaly, it's the likelihood. So it's likely in March to be a little cooler than average up in the northeast, and very likely in March to be warmer than average, to continue to be warmer than average in the west. We know that last month was cool. And we can look out the 90-day time horizon, March, April, May, and there's this prediction for continued warmth in the west in Alaska, and maybe a little bit cooler than average in Texas. So using the time history of what's happened so far, what we know about what's already happened and what is happening, plus the forecast information, I put together for you this qualitative map of what we're saying. Early in the west, and this prediction for the west, I admit, is maybe not very exciting because it's already happening. We did make it at least a few weeks ago before it was definitively happening in the west. Late-ish in the southeast, just because it might take more time to get over the inertia from having such a cool winter for some of these states. And then average. So what's average for this region? It's basically, for the leaf index, it's basically April. And for the bloom index, for the bloom of lilacs, it's basically first part of May. So that's our forecast. And we might be wrong. We might be right. We won't know until we go through this one realization that actually matters, the realization of this season. We're going to try to get your observations in there to weigh in on how we're doing. And we're going to wrap it up in May with another webinar, and I'll report back on how we're doing. I'd love to get emails about this kind of thing from people. I'd love to hear what you think about how this process is going and whether it's useful or maybe if we're missing things, what we're missing. And if you're not an observer yet and you're thinking about it and you're on the fence, this is sort of it would have been really great to have worked as an NPR campaign manager at some point to try to motivate action here. There are two options here for those of you who are not yet observers but are considering it. It's very easy. If you've got lilacs growing in your own yard, you can go to this web address, and this is all going to be posted. Or if you just Google NPN Nature's Notebook or Nature's Notebook lilacs, you'll get to this page. You can register as an observer of lilacs, common lilac, in your yard, which is what I have. And if you're interested in the clone species of lilac, you can purchase them. You can purchase a pair for $20. They'll be able to be planted in your yard, and then you can monitor this plant through time. One of the great things about the clones, and a lot of this spring onset, spring index work that Mark Schwartz pioneered and that I've worked on and others have worked on, one of the really interesting things about the clones is that it's kind of like you're taking the same plant and growing it all over the place, growing it everywhere, which is really, really a unique opportunity to study the effects of weather, because it's like you're controlling for the genetic differences and maybe other differences related to the plant, and you've got almost the same bush. I mean, it does change a little bit by its environment, but it's almost like you've got the same bush all over the place. So either of those options are great ways, I think, to be part of what I see as being absolutely critical tools for adapting to and responding to climate change as it unfolds this century, for making more skillful predictions, for understanding the underlying dynamics of the climate system, both as it evolves this century and even as it has evolved over the past. So thank you all very much. And these are some other people that I wanted to thank. And if you're on the list, you know who you are, and you've contributed to this overall effort. And I really do appreciate it. And that's all I've got. Thank you so much.
Thank you, Toby. That was fantastic. That was really wonderful. We'll give you a chance to get a drink of water if you like. And we have a couple of questions here coming in. Sounds like there was one clarification.
Sure.
Somebody wanted to make sure that when you were saying genetically identical lilacs, you were meaning the cloned lilacs.
The cloned lilac, yeah.
Yeah. Yep. When plants are cloned, that means that some piece of the plant some piece of a plant is broken off or cut off or whatever, and then grown into a new plant. So the two actually have exactly the same genetic material. So that is correct. There's one question.
And I should say too, I mean, the idea is that we get the week right. Now we're forecasting down to the day for precision, but really, if we get the week right and things move around, maybe the clones happen earlier one year, and the common lilacs happen later, but it's started in the same week or 10-day period, that's pretty good as far as we're concerned. So we're really shooting for that window, that period of time in the year when you feel that transition into the warmer, better days of spring.
Perfect. Okay. Here's a question for you. How is ground temperature used as a component in the model development?
We haven't put it in there yet. One of the things that we think this could be really important in is whether or not there's snow. So think about high elevation mountain regions, and where snow is going to reflect off a lot of that energy. Ground temperature is less responsive, obviously less responsive than the atmosphere. It's just got more thermal inertia. So I think that the signal of those warm pulses, if I remember correctly from some information that Mark Schwartz gave me a while back, the effect of those warm pulses is weaker than you would see in an atmosphere-only type of model. And you could think about this as the difference between dropping a quarter into water, right? So this would be like a pulse of warm air, drop a quarter into water, and it makes waves. A warm pulse of air in the atmosphere, you might see the ripples in certain plant responses. Whereas if you're dropping a quarter into honey, it just kind of plops, and that might be the sort of more of a good analog for the ground temperature response.
Excellent. Thank you. You're so good with the analogies.
I make analogies like a baker makes bread.
So, Toby, can the spring index model be used for forecast in mountain systems? And if not, why not? What would be the kind of data that you would need to improve the model in mountains?
That's a great question. So one of the things that we need to improve for doing mountain systems is topography. The way that we've laid out the grid, the grids that we're using right now for the predictions are very coarse. Think of that as being very pixelated with very large pixels. And that means that we're not resolving some of those critical topographic variations with elevation. So that's one thing. That's like, I would say, a zeroth order thing to do. We've got an unofficial product that we're not publishing yet that we're working on to get up at higher resolution stuff. It requires some more work and time. So that's not the one that we're putting up there, but we are working on having a very high spatial resolution version of the forecast, the springcast. That's one part of it. The other part actually does have to do with the dynamics. And this is a great question because if you think about what's happening at the higher elevations, especially in the southern part of the Rocky Mountains, it's cold because you're up high, but you're in a weather regime, a domain of weather that's more similar to what's happening south. And what does that mean? Well, we don't really know yet. We don't quite know what it means to have these really cold sites that are experiencing the weather patterns, the circulation anomalies as they propagate through that are also affecting the lower elevation sites. So once spring is switched over in the lower elevation sites, and now the jet streams move way off to the north, what does it mean for the higher elevation regions in the mountains, especially the southern Rockies? And it's an open question. There could be some really rich information there, and it could be absolutely critical for understanding snowpack hydrology in the Colorado River Basin, which, as everyone knows, waters the plants for a lot of what's grown in the southwest of this country. It's a critical water source. So we absolutely need to figure out what this picture looks like in the southern Rockies.
Okay, Toby, I'll take this next one. There was a question from someone who's in the northwest United States about what alternative plants might we be able to use for lilacs than alternative to lilacs for the springcasting effort, because this particular person said that they have few lilacs where they live. For the current model, observations of lilacs, either cloned or common, are probably what are most appropriate at this point. However, we are definitely looking to try to extend the model to additional species too. And we have other campaigns that we're running currently through Nature's Notebook called the Green Wave campaigns that are broken down by region that emphasize maples, oaks, and poplars. And so, Linda, what you could do is check that out on our website and see what maple, oak, or poplar species we have interest in for the Northwest and see if any of those are available to you. That would definitely be a very valuable handful of species to pursue. And the Green Wave campaign actually extends across the entire United States. We just vary which species of maples, oaks, or poplars we emphasize in the different regions because different species are more common in different parts of the country, of course.
Yeah. No, I completely support that. That's a great answer.
There's
My
one
parents
other
live in the Northwest, so if they're listening, that's what you should do.
I think they are, Toby. There's one other species that I'll mention too. For those of you that are in the southeast or the southernmost states of the United States, we do have trouble growing lilacs down here. And what we've done is established or selected a cloned dogwood that grows well in the southeastern states. And we emphasize either cloned dogwoods, which is the Appalachian spring dogwood, or native flowering dogwoods, which is Cornus florida. And you can see those species available on our website too. That's another one of our campaigns that we're emphasizing, and we hope to be able to use the observations from the dogwoods to help supplement and extend the spring index model down into the southeastern states as well.
Yep. Yeah. So just to tag on there, one of the things that we have started to notice is that the variations in a lot of the species and a lot of the responses, not just species, but a lot of the things that happen in spring are pretty strongly governed by the very strong year-to-year changes related to the position and structure of the jet stream and how it breaks down in the spring. And so it's not perfectly analogous to everything moving together in concert, but it's kind of like a bus, like a noisy bus with a bunch of people on it moving around inside the bus, but the direction from one year, maybe it's a bus that's rocking back and forth. The similarities between the different responses within that package from one year to the next year seem to be pretty pronounced. The similarities seem to be pretty pronounced from one year to the next year. And that gives us a lot of hope for being able to extend these indices to things beyond the lilacs and the honeysuckles, which is what underpinned the model originally, but to the kinds of species that you're describing, and also to agriculture. And that's important, because if we could give better predictions of when the optimum window to start planting might be well ahead of when it actually occurs, that could seriously bolster our capacity to produce sustainable and nutritious food supplies here and really globally. So that's underpinning a lot of this, the idea that all of it moves together and we've got multiple species that we need to start building into this model.
Okay, here's a physics question for you, Toby. If I think I'm understanding this properly. The question is, I think it might be a clarification. The change in energy absorbed by human contribution to existing greenhouse gases is 2 watts per meter squared?
Approximately, yeah. The radiative imbalance from human activity is 2 watts per meter squared, about, at this point. Yeah.
Okay. Let's see. I'll take this one. Someone asked, how do we know for sure that the clone lilacs will not become destructive invasives in some environments? And that's a really good question. We don't actually know that for guaranteed positive sure. We never know that when we start moving species around to different parts of the world. We used to have, as Toby mentioned, a honeysuckle that was planted and observed as part of the construction of the Spring Index model way back when, and that's since been dropped, and we no longer recommend people plant and observe them for that very reason, that they actually are pretty invasive. They kind of take over and force out some of the other native plants in different environments. And so I don't know for sure that anybody's done any real extensive research on this. However, I guess I would say that we've been spreading this particular clone of lilac around the country for more than half a century now and haven't really run into any major detrimental impacts. And so we might be naive to assume, but I think we're kind of operating under that assumption that it seems like it's not too invasive or problematic at this point. And so at the present, we are continuing to encourage people to plant them. Also, I think it's sterile. Can either of you guys confirm that? I thought I remember hearing that it was a sterile plant, and so it wouldn't. There. Okay, great. I just had confirmation that they will not grow a bunch of additional babies and spread all over the place. So that's great. Let's see. Toby, I'm going to kick this one to you. How do you separate influences of temperature from soil moisture, day length, elevation, and so on when looking at phenophase timing?
That's a huge question, and it's a really good one. And I'm not the only one working on it. There are several others who are part of this larger research group. And I would say the best answer is it's a work in progress. I think one of the most critical pieces of this puzzle that we need to start working on, and we are working on, in fact, is separating out the terms, the parts of the budget. So if you think of the economy of temperature, the total temperature anomaly, or the amount of energy you have from temperature and radiation from sunlight has to be partitioned apart into soil moisture, export, latent heat export. In other words, some of the energy coming in from the sun and some of the energy from the warm air is going to leave this region that I'm in for somewhere else just because it evaporates water and that water vapor goes somewhere else. And we, at this point, we've got a very, I would say, a good but somewhat crude approximation of the energetics that's proven to be pretty good for lilacs and honeysuckle so far, and for characterizing this warm pulse in the beginning of spring and the accumulation. It's a widely used metric. It's the growing degree hours or growing degree days. It's also very popular in agronomy. But we do absolutely need to do a better job of separating out what it means to have warmth, because it's not just one thing. Warmth, which we experience as one thing, should be divided out into warm air that's being pulled in from southern regions, warmth that maybe occurs locally just because in some cases, some years you might have snow, and the next year you might not have snow. Well, if you have snow, that reflects a lot of energy out into space. If you have no snow, you can absorb that energy. Those are two, and then the third one is how much of that energy is lost to water vapor. That's a really active, critical area for research.
Okay, thank you. Here's another one. Hopefully this is an easy question. Is the sheet you showed basically the height of the boundary layer? And if not,
almost,
how?
Yeah, it's the 200 millibar height for those of you fans of Reanalysis Data. It's the 200 millibar height. So it's not quite the top of the tropopause, not quite as the troposphere is part of the, that's where we live. We live in the troposphere, the lower part of the atmosphere, the troposphere. It's not quite the top of that, but it's getting pretty close, and it's where the jet stream is really active.
Super. You've got some technical...
Anyone who's flown east or west is familiar with this. So if you go fly from San Francisco to New York, it's faster. And that's probably because you're riding along with the winds, whereas in the opposite direction, it can be a lot slower. My mother said that she flew recently from the Northwest to Alaska, and it took 2.5 hours longer to get to Alaska than it took to get back. And it just reflects the jet stream and the upper level winds, which are really strong. I mean, sometimes as much as 200 miles an hour at that height. So, so that's why we use that sheet at that place, because it really is a good proxy for where the jet stream is. And the ripples in the sheet are usually going to correspond to ripples in the jet as well, waves.
Okay, here's a follow-on then to that. So it does not really address how the PBL, is that something boundary layer, moves up and down during seasons and affects mountains?
Not directly. No, it doesn't. It doesn't. The PBL, is that right?
Yeah.
PBL. Yeah, it doesn't. It doesn't address that. No.
Okay. All right, I'll give you a break and I'll take the next one. Oh, planetary planetary boundary layer. Thank you, Georgia.
Okay.
I
All
did
right.
not know what that was. This person said when she first signed up for Nature's Notebook, she looked at lilacs, but the area map on our lilac page showed that her location was outside of the clone lilac region, even though they grow common lilac there. So she didn't choose the common lilac in her yard to watch because she thought it wasn't a good indicator. And this is Western Oregon. And I just want to encourage her, you, Jody, or anyone else, you're welcome to submit on lilacs. And actually, maybe we should consider revising that map or specifying on there that that's generally the distribution of where they're found most commonly. But for sure, you're right. They grow in Seattle and Western Oregon and kind of all along the coast. And we even have a few in higher elevation areas down here in Arizona, which definitely isn't represented on the map. But the observations from those locations are just as valuable and important to helping construct and validate the models that Toby is presenting and working with here as any other location. So thanks for pointing that out, that actually can be a deterrent. We don't want it to be, actually. Toby, is there a reference for the 2 watts per meter squared determination? Going back to the...
Yeah, it's in the IPCC.
Pardon?
It should be in the IPCC.
Okay. We can make sure that that makes it out in the follow-up documents for this. Someone was looking to actually cite it in a NEPA document, so we'll make sure we get to the appropriate citation for that. Toby, you and I can decide who wants to cover this. This particular person says that he's planted aspen groves using aspen starts from distinct locations geographically and from different altitudes. And the differences in the leaf out from those groves, grown from those starts from different locations, can be up to a month difference. Is it safe to say that leaf out is genetically driven in the groves? What do you think?
That's really hard. What do you think?
I think would be inclined to think it sounds like it.
Go ahead. What I was going to say, what would be interesting to see is if, okay, so there's this systematic offset, but how do the year-to-year variations track each other? Because that would be more like the footprint of the atmosphere.
But if you have one grove consistently behind, lagging behind the other, then it might indicate that they're adapted to slightly different conditions and so have slightly different triggers that they're looking for. which would reflect some sort of adaptation to genetic.
Yeah, if they're not very well correlated, if they're always kind of a month off, but it goes between 2 weeks and 6 weeks. You know, if it's an average of a month, then there'd be differences there. But if it's like 1 year to the next year, it's all later, it's all early, but they're still offset by a month, then that suggests a much stronger role for temperature and for the climate atmosphere system.
Yeah, it's a really good question.
Pacing those variations.
That's a really good question, and actually a really good justification for why we encourage folks to submit observations, especially from the same locations from 1 year to the next, and ideally even the same individual plants from 1 year to the next, because that allows us to kind of isolate those differences and control for that variation from one plant to the next and from one location to the next. Okay, that covers the questions that we have that have come in, and it looks like we're about out of time anyway. So Toby, I think we will let you go. Thank you so much for taking the time.
Thank you. Thank all of you.
With us all. And thank everybody who has hung in here for this webinar. I feel like it's been really, really valuable. And it's going to be super exciting to see how things really do play out this year. And I, for one, am really excited to see what you're able to share with us in May. Maybe I'll check the date on that real quick. That webinar where Toby will follow up with us is actually scheduled for June 1st, 2 p.m. Eastern.
So at the end of spring for most places. The mountain regions might still be waiting, but other than that, unless it's really an exceptional cold year, we should be able to say quite a bit about what has happened between now and the beginning of June.
Okay. Well, thanks again.
So this is the beginning, in other words. Well, thank you.
We'll post the copy, the recording from this webinar on our YouTube page, hopefully in the next day or so, and we'll try to summarize the answers to the questions that came up and post them as well. Thank you all again. We'll talk to you soon. Bye-bye.